All right, let's jump right in. Have you ever looked at a really complex system and just wished there was a secret easy mode? Well, in the world of linear algebra, there kind of is. It's a super powerful technique called matrix diagonalization. And trust me, it's all about finding the hidden simplicity in really complicated situations. So why should you care? Well, imagine you need to apply some transformation, represented by matrix A, 100 times. Look at the left side. The hard way? That means multiplying that matrix by itself 99 times. That is a total computational nightmare. But now look at the right. If we can diagonalize that matrix into a new one, D, the problem becomes, well, almost laughably simple. You just take the three numbers on the diagonal and raise each one to the power of 100. That's it. We just turned thousands of operations into 3.
And that really is the million-dollar question, isn't it? How do we get from that messy, complicated matrix on the left to that beautiful, simple one on the right? The answer, it turns out, is all about finding a new way to look at the problem.
You see, it turns out that a lot of matrices have these built-in magic directions. And if we can find them, well, that's the key that unlocks this whole thing.
So what exactly are these magic directions? They have a fancy name, eigenvectors. Here's the deal. When you apply a matrix to most vectors, they get knocked around, stretched, squished, and rotated into a totally new direction. But not eigenvectors. Oh no. Eigenvectors are special. When you hit an eigenvector with a matrix, its direction stays exactly the same. The only thing that changes is its length. It just gets stretched or shrunk.
I love this way of thinking about it. Picture the matrix as this machine that's twisting and transforming space. The eigenvectors are like the fixed rails of that machine. They are the directions where all the twisting and turning goes away, and all you get is a simple scaling.
And that scaling factor, it has a name too, the eigenvalue. It's usually written as the Greek letter lambda. So if an eigenvalue is 2, its eigenvector gets doubled in length. If it's 0.5, it gets cut in half. It's just a single number that tells you exactly how much of a stretch or shrink happens along that magic direction.
And this right here, this is the big aha moment. Diagonalization isn't about changing the problem. It's about changing your point of view. If we can just shift our perspective and build a whole new coordinate system using these magic eigenvector directions as our axes, our super complicated transformation suddenly becomes incredibly simple.
So, how do we actually do it? Well, it's not just waving a magic wand. There's a tried and true 5-step recipe that gets us there every time.
Here's the game plan. First, you find something called the characteristic polynomial. Think of it as a special equation that holds the secret code to our eigenvalues. Step 2, we solve that equation to get the eigenvalues themselves, our scaling factors. Then, for each of those eigenvalues, we hunt down its partner, the eigenvector, our magic direction. Finally, we just bundle them all up. The eigenvectors get collected into a matrix we call P, and the eigenvalues get put into that simple diagonal matrix D.
And it all comes together in this legendary formula. A equals P, D, P inverse. D is our simple, diagonal, easy mode matrix. And P is our change of perspective matrix. It's what translates our problem from our normal world into the simple eigenvector world. We do our easy calculation there with D, and then P inverse translates the answer right back. It's brilliant.
Now, I know this might seem like a really abstract math puzzle, but it's not. This one idea is actually the engine running under the hood of some of the most important technologies that shape our world.
I mean, just look at this list. Google's PageRank algorithm, the thing that basically organized the internet, it works by treating the entire web as a gigantic matrix and finding its most important eigenvector. In machine learning, it's how we find the hidden patterns in massive data sets. It's even used in quantum mechanics to describe the fundamental nature of reality. It's everywhere.
And we are not talking about little 3x3 matrices here. That PageRank algorithm applies these exact same ideas to a matrix with more than 1 billion rows and columns. At that kind of scale, turning a hard problem into an easy one isn't just a nice trick. It's literally the only way to even find an answer.
But there's an important catch. As powerful as this is, it doesn't work for every matrix. Sometimes the magic just isn't there.
So a matrix is only diagonalizable if it has enough independent eigenvectors to create a complete coordinate system. If it doesn't have enough of these magic directions to span the whole space, we call it a defective matrix. These guys often have a shearing effect, and you just can't find enough directions that aren't getting rotated.
So why does this happen? Well, sometimes an eigenvalue pops up more than once when we solve our characteristic polynomial. For this to work, we need to find a unique, independent eigenvector for each of those repeats. If we can't, if a repeated eigenvalue only gives us one magic direction instead of the 2 or 3 we need, then the whole process breaks down. We just don't have enough axes to build our new, simple world.
So, when you boil it all down, diagonalization is this powerful reminder that sometimes the most difficult problems become simple once you find the right way to look at them. And that kind of leaves us with a final thought, doesn't it? What other complex problems in science, in technology, maybe even in our own lives, are just waiting to be simplified if only we could find their magic directions?